take a look at our exponential equations. Starting with a very simple one, 5 to the power of x equals 125. Then we know, okay, 5 cubes 125. No big deal there. Then we step it up a bit, something like this. 4 to the power of 2x plus 1. Well, we can write both sides as 2 to the power of something, and then equate the powers and we get our answer. Again, not a huge problem. But then we get something like this. 7 to the power of x is 32. And that's a little bit more involved because there's not a nice, neat answer to that that's obvious. And that's where we make use of logs. Remember, our definition of a log means we can rewrite this as log 32 base 7, whatever that happens to be. Now, some calculators will work out base 7, some of the newer ones, but most of the older types only have 2 log buttons, the base 10 and the natural base. That's why we have our change of base formula. Well, it's not the only reason why, but it's one of the reasons why. We can convert it to a base that we can use. That would be the same as the log of 32 over the log of 7. It doesn't matter which log button you use for that, as long as you use the same one for both the top number and the bottom number. It needs to be the same base. So 3 to the power of x is 5 to the power of x minus 2. We simply log both sides. Again, in this case, the base does not matter which one we use. Playing around with it, we just want to make x the subject, and eventually we get it. And again, we can plug that into our calculator. Doesn't matter which log button we use, just use the same one, and we get 6.301. These sorts of exponential equations, they're actually quadratics, because we could rewrite that, and I'll do it via a substitution. I mean, you don't have to do a substitution. But essentially, we're saying that's m squared minus 4m plus 3. All right, I can work out what m is, substitute back in. 3 to the power of x is 3, or 3 to the power of x is 1. Well, we get 1 or 0. Just a word about inequations and solving them. So inequations, and when we're dealing with continually increasing or decreasing functions, so the piece of the curve is always going up or always going down. If you apply that function to an inequation, then the inequality sign is maintained if the function you're applying to both sides of the equation is continually increasing over that interval that you're playing with. And it's reversed if it's continually decreasing. Now, this explains why when you turn both sides of an inequality upside down, you change the inequality sign, because what you're really doing is applying the function y equals 1 on x. And y equals 1 on x is continually decreasing. So therefore, when you apply that function to the equation, the inequality sign swaps around. Also, when you multiply by a negative number, it swaps around. Why? Because what you are applying is the function y equals negative x. And y equals negative x is a decreasing function. So you swap the signs around. So keeping that in mind, if we get an inequality like this, or I should say an inequation, not an inequality, an inequation like this that we want to solve. Now the nice thing about our exponential and our log functions, they're both continually increasing functions. So I can apply that function to the equation. So I'll do the log. I've chosen base 2. Seems to make sense seeing our question is 2 to the power of x. But then that equation should be true. Well, in the middle, the log 2, base 2 will cancel. The power comes to the front, so I've got x. Log of 1 is always 0. And log of 32, base 2, well, 2 to the power of what is 32? Well, 5 is. And there's the solution to that inequation. So if I wanted to solve this inequation, I can apply the exponential to it, so the inverse of the log. Well, I don't know, you wouldn't necessarily write that line down, but to show you why that becomes x, because we're applying the exponential, we're saying 3 to the power of log base 3, well, they cancel out, leaving me with x on the left-hand side, so we get x is greater than 9. That shall do it.